Hi everybody, we are now moving on to reflection. This is 7.1. If you haven't done the reading, please at least read chapter 23 in Coletta. If you're in Physics 112, please read chapter 25. Okay. So we're going to be talking about reflection of light, and we had talked about some elements of that when we were talking about the nature of light in the last lecture, 7.0. The first thing that we need to talk about is how light actually, the rays of light are traveling during reflection process, right? So that's Fermat's principle of least time. So when light rays are reflecting off of surfaces, it's important to note that if it's the light ray, if it did take this hypothetical, this is not true, this is fake. I just created this slide to kind of illustrate why light actually comes in at the same angle and exits at the same angle. So why doesn't light take this path? This is not true. A true path of light. Not a true path of light. So why doesn't light take this path where it's more of a direct route, right? It goes from here, bounces down, and then goes straight across, right? So it's not bouncing as much, really. So why doesn't light travel like this when it reflects off of a mirror? Well, Fermat noticed that the angle that it comes in at, and this is called the incidence, this is the incoming light ray. It's called the incidence. And this is the incidence angle. It's going to be reflecting out. This is a reflected angle. This is reflected beam, or reflected ray. This is an incidence ray. So light is coming in, it's hitting a surface of a mirror, a shining object, and then reflecting out at the same angle. These two angles here are the same. So the incidence angle is equal to the reflected angle. Well, a lot of people ask, well, why is that true? Why is that? Well, if it takes this direction, if it would travel this way, which is more of a direct route, that distance, as you can see, if I've lined up those vectors correctly, they look that distance, right? Well, the red light ray is actually a shorter distance. It's actually a shorter time. It's actually better to say. So how Fermat reasoned that these two things are equal is that light actually takes the path of shortest time. Okay. So here is the anatomy of a reflected light ray. And again, we're not using a source, a point source of light rays, where the light ray is traveling in all directions, even though we know light, if you have just a light, like a light bulb or the sun or something like that, or a flame, it's going to be shooting out light rays in all directions. It's easier for us to analyze just single light rays. So we're going to have to be using lasers to do this. Okay? So when you have, it's important to note that with reflection, so that Fermat's principle of least time leads into the law of reflection, which means this: the angle of incidence is equal to the angle of reflection. Or what it'd say, the incoming light ray bounces off a surface and then reflects out at the same angle. Now, you're going to notice that the surface is right here, and there's this fake line. There's this fake line called the normal, and normal means perpendicular. Okay, normal. Not that there's abnormal and normal. Normal means perpendicular. Okay? So where the light ray actually hits the interface, that's the surface going from air to whatever this reflective surface is, that dot right there is the interface. Well, this line is the interface, and that dot is where it intersects with it, right? So the interface is this line right here, and the normal is a made-up line where it's at that intersection, right? So you do a dot perpendicular to that interface, that line of interface, and then you're going to get a perpendicular line, right? So that's what normal is, right? So this angle of incidence, this angle from the incident ray to the normal, is going to be measured in degrees, and that will be equal to the reflected light ray, which is the reflected light ray to that normal, okay? So the interface is this dark line right there, okay? From one medium, air, to glass. Okay? Well, when we're talking about plane mirrors and smooth surfaces, what we're talking about is specular reflection. It's reflecting the entire spectrum of light rays. So specular reflection is referring to a smooth surface or a plane mirror, or a surface where it's uninterrupted. There's no little waves or issues with that actual reflective surface, right? So the law of reflection really holds true with all surfaces. However, it's easier to analyze light rays when they're reflecting off a surface that's smooth, so we could see the specular reflection, okay? And again, the law of reflection has two components. The incident light ray and the reflector light ray are on the same plane and perpendicular to the surface, and that those two angles will be equal to each other. Now, there's another type of surface which is not specular. It's more of the specular surface will have specular reflection. A diffused surface will have diffused reflection. So if I zoom in on this, and we'll see if I can zoom in on this. Yes, I can. Neat. You're going to notice that this surface is really rough, kind of like waves on the ocean, right? Well, the reflection is still holding true. The law of reflection is still holding true. It's just that the surface is now changing, right? So if I drew the interface right there, and I'm drawing the normal, so I'm looking at this incident light ray and this reflected light ray right here, and you'll notice at that perpendicular I drew to that surface at that point, the incidence angle is equal to the reflected angle, right? And I want to note while we're here, incident light ray, reflected light ray, that if I note an angle here, if you use a protractor, this angle is going to be the same size as this angle, okay? If you put a protractor across this, you would have to just, you would notice that this angle would be the same size as this angle. Even though this looks like bigger, radially it is not, okay? In polar coordinates, okay? So my point is, if I draw one incident angle here at this point, I'm going to erase this, come on, I'm going to erase this guy right here. So if I draw one angle here at that one and draw another angle up here, those would actually be the same angles. This one to here would be the same angle as it to here if I drew it right here. It's just sometimes it's more easier to draw. Anyways, back to this. You could actually see that the law of reflection is still holding true on a diffuse surface. You just have to be creative in recognizing the interface from air to whatever this is, water. Okay, so this angle is equal to this angle. And even this one right here is coming off. If you notice that that one is going right there. So I'm trying to draw the normal. It's the dotted line. So that angle is going to be equal to that angle too. Okay. So it still holds true, this law of reflection. It's just with diffused surfaces, light rays are going to be kind of bouncing out at all different angles, but they're still obeying the law of reflection. Okay. So the thing about this is as long as so the wavelength of light and frequency are going to be constant. It's just the velocity and path that are changing when stuff is bouncing off due to a reflective surface, either diffused or specular. Okay. Well, there's some cool things that our eyes, it's kind of interesting how our brains perceive reflected images is actually interesting, right? So if you have if your eye is up here and you have an object right here, that object is going to be emitting light, or it's going to be absorbing, or light is going to be scattered off it, and then that light is going to hit that object and travel along this line and reflect off the surface at the same angle that it is coming in at and into our eyes. Well, our eyes don't know that there is a reflective surface here, really. And so we see things along a straight line. Well, it's interesting that what is happening here is that this distance, this object distance to the object, from the object distance is s, is going to be measured from where the object is directly to the reflective surface, and the image distance is from the interface or reflective surface to where the image along a straight line. So it's interesting that using the law of triangles here, that our brains will actually see this distance here. So this distance, we're going to see it as this distance here. So a good question is, what does a mirror actually do? Well, a mirror is just reflecting that surface, obviously, but it's actually interesting. How does it change your perspective? Well, we're going to talk about that in a little bit, but this is the main point of this slide right here, is that our brains will see that this distance, our image distance to the interface, is going to be the same distance as the object's distance to the interface along a straight line, right? A direct line to the interface. So that's one thing that's really cool, is that our eyes see that reflective distance the same as so if I'm looking at myself in the mirror, my image to the mirror on the other side of the mirror is going to be the same distance as my actual distance to the mirror, my object distance to the mirror. Okay? So this distance from here to here is going to be the same as the distance of the image to the mirror. Okay? Well, there's also an issue of magnification too, right? With plain specular mirrors, okay, with plain specular mirrors, the image that gets formed is going to be the same size as the object, right? So if I'm looking at myself in the mirror, my image is going to have my same height as I am. If I back up a step, well, it's still going to be my same height. I'm just a further distance away, right? So a plane mirror will give you an image that is the same size as your image. There's a one-to-one relationship, a plane or specular mirror. Okay. The other cool thing is that this image is going to be reversed. Okay. So if you're standing here looking at the mirror, what the mirror does is it actually takes this perspective pointing towards the mirror and reverses it to be pointing in the opposite direction of the mirror. And that's why a lot of people will say, well, it shifts left to right. Not really. What it does is it changes your perspective. By me looking in the mirror here, what I see is actually myself, my image looking back out at myself in the opposite direction. So it changes your perspective by 180 degrees. It changes my perspective from pointing this way all the way to being pointed to looking in the opposite direction. So your perspective is changed by 180 degrees in a mirror. It basically reverses your perspective from front to back along the Z direction. The Z direction, which is in or out of the mirror. So if I'm looking towards a mirror, it actually makes my my perspective in the mirror, my image is pointing back out in the opposite direction that I'm looking. It's not reversing left or right, it's reversing, and that would be the X direction. So this is the X direction, this is the Y direction, and this is the Z direction. Okay, so it's actually reversing your perspective along the Z direction in and out of the mirror by 180 degrees. Well, that is an interesting thing, okay? So there are some cool consequences to this. So that's one of them. So those are the three things. It's your distance to the mirror is one thing that a mirror does. It makes your image distance the same thing as that. It also makes magnification equal to each other. The magnification would be also, by the way, is the height of the image over the height of the object. So this is image height, this is object height, this is image distance over the object distance, right? So yeah. Anyways, so it's taking the heights of those two things, and it reverses your perspective along the Z direction. Well, knowing those three things is fine, but really, do we understand what a mirror actually is? Okay, and this question is a great question, because if you could spend your life looking at mirrors, and we all have, we have hundreds of thousands of experiences throughout our entire lives with mirrors, and a lot of us don't even understand how a mirror actually works, right? So this is a great question that gets right to the crux of it. So I really want you to think about your answer. So the question is this: what is the smallest size mirror that you would have to have, and this is supposed to be the mirror that you would have to have in order to see your entire body in the mirror? Okay. Do you need something, a mirror equal to your height? Do you need a mirror half your height? Or does the mirror size even matter? Is it just more of a point of distance to the mirror? Any size mirror will allow you to see your entire body in it. It's just you need to back up, back away from the mirror or walk towards the mirror. So I want you to pause the video and then answer this question, okay? Okay, so coming back to this. Now, before answering that question, I really want you to click on this link right here. But before you watch, and I changed the link here. So I know I changed the video a little bit, so click on this link that I changed and watch it between timestamps 6 and 9.13 minutes. It's a really interesting video. Okay. And go ahead and pause the video and watch. Pause this video and watch the attached video at Minds of Our Own, and watch it for 3 minutes and come back. All right. Okay, we're back. So hopefully you've got a really solid answer. And what you'll probably have noticed is that from that video, you'll probably now be convinced that, hopefully, that it should be half your height, which is really weird. How is it that you only need a mirror that is half your height in order to see your entire body? Well, let's think about it for a second. We'll do this in steps. Suppose you had your twin, who's exactly like you, who's standing at exactly the same distance from you to the window as you are to your window, right? Suppose they're right there, right, in that window. What is the minimum size window that you would need to have in order to see their entire body, right? Minimum size. Would it have to be like this, number 1, or number 2, a full body mirror without any interruptions at the bottom of the feet? Or is it something half the height? Well, if you look at it, their feet are emitting light coming off and going into your eyes, correct? And then their head is emitting light along a straight line and going into your eyes. Well, if you look at that, that mirror right there is about half the height of that person, of those two, and that window is right there is half the height of that. Same thing here. You don't, right there, so your twin is emitting light and going into your eyes, and this one is emitting light and then going into your eyes. Again, you only need a window that size, right? And I know you're saying to yourself, well, you're talking about a window, not a mirror. Well, it's the same kind of thing, okay? So number 3 is the minimum size window. If you look at it from this person is, your twin is emitting light and going into your eyes, and they're seeing the same thing. They're seeing the reverse of that light rays. Well, this is what's happening with a mirror as well. Your mirror image person, which is kind of like your twin, who's standing at exactly the same distance that you are, okay, what you're seeing is your light rays are coming off, the incident light rays are coming off your feet, hitting the interface to the mirror, and bouncing off at the same angle. This is the reflected angle. This is theta sub I, and this is theta sub R. You're seeing that angle. You're seeing those two things as the same angle, right? And how you're seeing your head is the top of your head is emitting light, or scattered light is hitting the interface and then coming back in at the same angle. So that's how this image forms over here. Well, actually I should just circle this. So that means you really only need a mirror that is half your height. Okay? And so what that means, so how come when you're standing in your own bathroom that you can't see your feet? Well, that's actually because you have your sink and everything that are blocking your path of light, right? So your sink is coming out from here and hitting right there, right? So this is your little sink. Well, that's blocking your feet. The only way to actually see your feet would be to back up. But as you saw in the video, Well, now you'll be able to see it coming back into your eyes. As you saw in the video, if the sink weren't here, it doesn't matter your distance to the mirror. If the sink weren't here, then you would be able to see. You wouldn't have to back up to remove the sink for the light rays to avoid hitting the sink. If the sink weren't here, you'd be able to stand right up against this mirror and be able to see yourself. So now let's continue on, and we're going to do some more reflection problems. And some of these are about how many objects do you see in the mirror. So let's go ahead and take a look at this, and let's do the middle one right here. So what would Alex see in the mirror? And here are Alex's little eyes right here. So would Alex be able to see object number 1, which is a light source, object number 2, a light source, number 3 is a light source, number 4 is a light source. Now this is a wall and you can't see through it, okay? This is the mirror up here. So what would which of these objects would Alex be able to see in the mirror from his vantage point if he was looking straight forward at the mirror? So pause the video, think about it, and you're going to have to draw ray lines, and you'll have to draw ray lines with the reflection angle, the refraction angle, incident angle, reflection angle, and draw the normal, which is a perpendicular to the interface, which is the surface of the mirror. Okay? So pause the video and try it out now. All right. Well, the best way to do this is to essentially just find the midpoint between Alex and any one of these objects. So let's try number 4. So the midpoint between Alex and number 4 light source is about right here. And what I'm going to say is this. Excuse me. So the number 4 light source is going to have a line, and it's going to be kind of a straight line right to the light source, okay? And then here is going to be the normal, and the interface is right here. It's horizontal, the normal would be vertical. And if you notice, if I drew that ray to Alex, the reflection ray, and I think I actually have it off a little bit, so let's try erasing this. Try it again. It's kind of hard to eyeball this. So maybe I think the midpoint is going to be right about here, because it kind of looks like this. Yeah, that's probably closer to the mid thing. So this is the incident ray. The rays are coming up from the light source and going down into Alex. So the reflected ray, which is this one, going into Alex, and the incident ray should be equal-ish, hand drawing this. And if you notice, it gets hit by the wall. And what you find out by doing this, and by trying new lines, I'm going to use a different color. I'm going to try red, right, for this. And it looks like if I try to do number 1 just kind of clears it. Really close. It's cutting it close. So essentially what I'm saying is this. 4, 3, 2, and 1 are, 4, 3, 2 are going to be the reflected angles and refracted angles. This is too big of an angle for it to hit into Alex. Number 1, if he's going to see any one of these, it's going to be the number 1. Okay? So I'm going to try to draw those. So Okay, let's go ahead and try mirror. How many of these lights is mirror going to see? I'm going to scroll down a little bit, and we're going to see mirror. How many lights is mirror going to see? Well, you go ahead and try it, and let's see what you do. Let's go ahead and pause the video and try drawing some of those, okay? I think it might be more than what Alex sees. All right. Well, again, light source number 4 is going to come up. I'm going to try to draw the bendiest one right to here. Straight line, just nicking the edge of that. When I draw that, that looks like maybe that might be number 3. So I think number 3, number 2, and also maybe not number 1. No, not number 1. It looks like only numbers 1 and 3 are going to be able to hit that. Number 1 is at too harsh of an angle. So let me go back and I'll redraw it. Let's try number 1. Number 1 is going to come up. It's going to nick the edge of this, and if I do that, it's going to barely, and it looks like it's going to just miss Maria. So number 1 is not going to happen. Let's try a different color. Number 2 looks like if I draw number 2 and I nick that edge there, it's going to then hit Maria. Okay, so it looks like number 2 is going to happen, but not number 1. And number 3, I'm going to draw that. And it looks like number 3 is going to work. And now if I try number 4, I'm going to try number 4 with kind of pink. Let's do pink. No, let's do green. Number 4, let's try this. It looks like number 4 actually might work. It's hard to tell. For sure, though, out of all these, actually I think if we do number 4 there, it might work. So out of all these, which won't work from the reflected angle is black. So number 1 will not work. Looks like number 2, 3, and 4 might be a reflection in the surface. So this is basically how reflection works. Okay? And that was reflection with 1 mirror. It gets even more complicated with 2 mirrors, because now you have 2 reflective surfaces, and then you're going to have normals to those. So how do you deal with that? Well, let's go ahead and mark up this document just like we normally do. And then here we go. So if you think about it, this one's already pre-marked up, but you have an object right here at P, right? So according to this already pre-prepared document, what you have is you should have P1, P3, P2, okay? All right, so on top of the existing object itself. So what's happening is you'll see P right here. The image bounces off this mirror, bounces off this other mirror, and then goes into your eye right here. So the interesting thing is your eye will see an image formed over here at P3 due to the second this reflective surface. But not only that, it's actually going to see an image formed at P1 due to this other image. Okay. right? So P1 and P3 will form from this these two bounces that it occurs. So it's kind of really interesting because this image right here, the object right here, forms an image P1 that bounces right here, but it actually forms a second image P3. So this P3 right here is the image of P1 formed twice. P1 will form here, but it also will form over here. Okay, this image right here, P2, right here, is going to be formed just from the second mirror. Okay, so this object P is going to bounce off. It's going to bounce into. It's going to bounce across here. Okay, bounce across there. So it's going to come out, bounce across there, and then bounce into your eyes. So what's going to happen is P2 is going to be happening because it's bouncing off the first mirror and the second mirror, and then into your eyes. So what you have is a total of 3 images gets formed. Okay, when you have 2 mirrors. So it's really interesting. And here's a more detailed version of what is happening. So how many baseballs, again, this is the same kind of problem. So how many baseballs would happen, would you see? So you would actually see 1, 2, 3 images formed here in this way. So you would see quite a few images get formed in this case. So you would see the same number, it's just kind of reversed in direction. So when you have multiple mirrors and you have when you have one object right here, what will happen is you'll probably get 3 formations. Well, go ahead and try out the lecture tutorials and the labs. I think there's a small lab associated with this, and there's some homework problems associated with this within Sapling. So please try it out, and good luck.